Welcome to this lesson on types and variables. As your programs run, they're going to need to access data. Programs use variables to store data. You might have one variable that stores your username, a second variable that stores your user's age. Each variable must be a specific type, such as an integer variable that stores counting numbers 1, 2, 3, 4, 5, or a floating point variable that has a number with a decimal point, such as 3.14. In this lesson, you're going to learn how to create, assign values to, and later access variables. Let's get started. So programs are going to store data within variables, and we have to tell the C compiler about each variable we want to use. Typically, we'll put our variable declarations, where we specify the variable's name and the variable's type, at the top of our functions. So in this case, we'd put them following the int main void, that open right brace. We'll put our variable declarations, and then we'll have the rest of our program statements. So if we look at this program, it's declaring 3 variables. They're all of type int. We have one that will store the student's height, one that will store the student's weight, and one that will store the student's age. So this program doesn't display any output or anything. We're just showing how you would declare variables. You can see that our variables start after that opening right brace. Each variable we create has a specific type, such as character, which can store a letter of the alphabet, integer, which can store counting numbers, such as 1, 2, 3, 4, 5, floating point numbers, which have numbers with a decimal point, and then double precision floating point numbers, where we want to store really accurate representations of a value. And so when we declare a variable, we specify its type and its name. The type will specify where the set of values the variable can store, and it will also specify a set of operations we can perform on the variable. It makes sense to do addition and subtraction on numbers. It doesn't make sense to do addition and subtraction on character strings, for example. And so a type defines a set of values and set of operations. C has 4 basic types: char, int, float, and double. And we're going to use these types as we create variables throughout this lesson. After we create a variable, we can assign a value to it using the C assignment operator, the equal sign. So in this program, we create 3 variables, one named height, one named weight, one named age. You can see that each one is the type int. Int is short for integer. It's going to store a number without a decimal point. So to assign the height 73, you can see that we have our height variable name, the assignment operator, and the value we want to assign. Likewise, we assign a weight of 180 and an age of 30. Again, this program doesn't display any output. We're just showing how to declare and then later assign a value to a variable. When we declare variables, we can put each one as individual statements. So in our first program, we declare a variable of age, the next statement declares a variable of weight, and then the third declares a variable of height. C also allows us to declare variables of the same type, meaning all ints or all floats or all chars, on one line separated by the comma. So in this case, we're declaring 3 variables, age, weight, and height, and they're all of type integer. When you declare variables, it's good practice to put a comment next to the variable's name that tells someone reading your code more about the information the variable is storing. So in this case, we're declaring our 3 variables, age, weight, and height. But then we have comments next to them that describes the variable. Age has the user's age. Weight has the user's weight in pounds. So this tells us that we're storing pounds as opposed to kilograms or something. And likewise, height is in inches. So we don't think that, okay, this is the user's height in feet or the user's height in centimeters, but we know what's the value the variable is going to store by reading the comment. So it's good programming practice to put a comment next to your variable declarations. When we declare a variable within our C programs, the C compiler lets us initialize the variable at the same time. So in this case, we're creating the same 3 variables, age, height, and width, or weight, but we're assigning values to them at the same time we declare them. Programmers refer to this as initializing the variable. As you've learned, C allows you to declare multiple variables of the same type on the same line. In this case, we're declaring 3 variables, but C also allows us to initialize those variables when we declare them. So even though they're all on the same line, we're creating a variable called age and assigning it the value 30. We use the comma operator to separate our variable declarations. We're assigning weight the value 180 and height the value 73. And again, all variables in this case are of type int. When you declare a variable, you have to specify the variable's type, what kind of value it's going to store, as well as the variable's name. So in the first case, we create 3 variables called A, B, and C. The second, however, uses more meaningful variable names: test underscore score, student ID, and hours worked. And so our first 3 variables weren't very meaningful names. Another programmer who's reading our code is going to say, what's A, what's B, what's C? But in the second case, because we've used meaningful names, it'll be much easier for someone reading our code to understand it. So as you declare your variables, try to pick meaningful names that to someone reading your code is going to make sense. The C programming language, like other programming language, has a set of keywords that have specific meaning to the C compiler. We'll use each one of these keywords throughout the lessons of this course. They're sometimes called reserved words. That means we can't use them for a variable name. If we try to, and in this program we're creating a variable called switch, when we run our program, we'll get a compiler error. That's because switch is one of our key words, and it has special meaning to the C compiler. And so it won't allow us to use a key or reserved word for a variable name. So many of the variables that we create are going to be of type int. Int is short for integer, and an integer value is capable of storing positive and negative counting numbers, meaning numbers without a decimal point. So -3, -2, -1, 0, all the way up to some size. The size of an int variable is determined by the C compiler, and the size will determine how large a value can we assign to a variable of type int. And we'll see an example of when we try to store a value that's larger than an integer variable can store, what happens. Variables of type char are capable of storing a byte of data. So the values -128 to 127. Normally variables of type char store an ASCII character, such as the uppercase letter A or the lowercase letter Z. We'll use character variables throughout to store things like a letter of a person's name. Variables of type float store floating point numbers, meaning a number with a decimal point, such as 3.14. Normally, a floating point number has about 7 digits of precision. So we have the number 1.234567889. So a floating point number, a number with a decimal point. But the C compiler only has so much memory to allocate to a variable of type float. And so even though we've specified 8 digits following our decimal point, the C compiler can really only store about 7 digits of precision. So the first 7 digits following the decimal point will be meaningful. We'll take a look at some examples of how precision can impact our programs. A double precision variable, a variable of type double, is about twice the precision of a variable of type float, hence the name double. It typically has about 14 digits of significance, meaning the compiler can accurately store a digit with 13 numbers to the right of the decimal point. And we'll take a look at that in a future program. So just as we can initialize variables of type int when we declare them, we can also do that with floating point variables. This program declares a variable named pi of type float and assigns it the value 3.14159. It then declares a small variable using exponential format, and then declares a double precision variable. And we've learned that a double precision variable is going to be more precise than a variable of type float, but it also takes double the amount of memory of a variable of type float. As you examine C programs, you may find what's called a type modifier that precedes a variable's type. In this case, we had an integer variable called current inventory, but it's preceded by the unsigned type modifier. We're going to take a look at these modifiers in detail, but essentially the unsigned says I want to store an integer value, so a counting number, 1, 2, 3, 4, 5, and I'm going to use only unsigned values, which means only positive values. In this way, it can use what's typically used as a sign bit, is it a positive or negative number, to increase the size of the variable so it can store a greater range of numbers, but they're only going to be positive numbers. As our programs execute, internally the CPU has special storage locations called registers, and it can access those very quickly. And so we may have a variable that we want to use over and over and over, and so rather than have the program store it in RAM, we can tell the CPU, store it in a register because we're going to use it a lot and I want you to be able to get to it quickly. And so that's the purpose of the register modifier. You don't see it used very often anymore. And then finally, there may be times where we have an integer value, a number without a decimal point, but it's a very, very large number. And so it's larger than what a variable of type int could store, maybe the country's debt, for example. And so we use the long specifier to tell the C compiler, this is going to be a big number. I need you to allocate more memory to store it. So we talked briefly about the unsigned modifier. When you use the unsigned modifier, you're telling the C compiler, I'm only going to store positive numbers. So I can't store values such as -1, -2, -3, because the variable doesn't have a sign bit that says it's positive or negative. It's unsigned. It can only be positive. And again, we talked about the long modifier, which we use when we're going to have an integer value, but it's just a very large integer value. It's bigger than what a variable of type int could store. So the long modifier tells the compiler, allocate more memory to store this value because it's big. And so in this case, we're declaring the national debt. And we've got a $30 trillion number. So it's a very big number. So we're using the long int modifier. Notice at the end of my number, I put the letter L. That tells the compiler, yes, I mean a number this big. It needs to be stored in a long variable. In this case, we're combining two type modifiers, unsigned long to our int data type. So this is telling us we're going to have a very big number, but it can only be a very big positive number. And behind the scenes, the C compiler will allocate enough memory to store that number. And again, you won't see this all the time, but as you look at other programs, you're going to say, what's this unsigned long, or what's this unsigned int? And they're just modifiers that's telling the compiler, I need to store something special. And so, in this case, I'm only going to store positive values, and it's going to be a very big value. And we've talked about the fact that a long value can store a very big number. And when we assign a value to it or reference it, a lot of times you may encounter the L. And that's telling the compiler, yes, this is a big number, it's a long number. And so we include the L at the end of our digits. And again, we talked about the register modifier. It tells the compiler, we're going to be using this number a lot, this variable a lot, so try to keep it in a register as often as you can. And again, you don't see this as often in today's programming code, but if you look at an older C program, you may see the register. And all that's telling the compiler is make your best effort to keep this value in a fast storage register as opposed to RAM. So a data type tells the compiler a set of values that a variable can store, as well as a set of operations we can perform on the variable. The compiler is going to determine how big or how much memory to allocate for each variable. And older compilers may allocate 2 bytes for an integer variable, where newer compilers will allocate 4. The short int modifier tells the compiler this variable is type int. It doesn't have a floating point, so a counting number, -1, -2, 0, 1, 2. And so it's an integer value, but I want to store it in as small of integer as you can. Typically, this will allow us to store values in the range -32,768 through 32,767. If we assign a value outside of this range, our program will have a logic error. And so every type specifies a set of values that the variable can store, as well as a set of operations. The short int says, use a small amount of memory to store this integer. When we use type modifiers, we don't necessarily need to specify the int. It's kind of assumed by the compiler. So we can say short int year, or we can say short last year. And to the compiler, they're both going to be the same. So just as we have an unsigned modifier that tells the compiler this variable is only going to have positive values, let me use the signed bit to increase the value range that it can store. We also have a signed modifier, which tells the compiler, no, this may contain negative as well as positive values. Also tells another programmer who's looking at your code that this variable may contain negative values. The signed is typically the default, so we normally don't see this modifier. So we've learned that when we initialize or declare a variable, the C compiler lets us also initialize it at the same time. So in this case, we're declaring three variables: counter, sum, and value, and we're initializing each one of them to 0. We've learned that the C compiler also lets us declare and initialize multiple values on one statement, separated by the comma operator. In this case, we're declaring three variables: count, sum, and value, and so you can see that they differ from the previous ones because they're using uppercase letters. The C compiler treats upper and lowercase letters differently, so the variable sum in lowercase is different than the variable sum in uppercase. That could be confusing to someone reading your program, but you just need to be aware of the fact that in variable names, upper and lowercase letters matter. But we're initializing all three of those variables to the value 0. And so it's going to create a variable called count, initialize it to 0, a variable called sum, initialize it to 0, and a variable called value, initialize it to 0, all in one step. Now there may be times as your program runs where you need to assign a variable of one type, integer for example, to a variable of type float. And when you do that, the C compiler has to make a determination of how do I translate this value. And so a floating point value has numbers after the decimal point. An integer value just has whole numbers. And so it may be compiler specific, meaning one compiler may do it slightly different than another compiler. Ideally, the standards will have them do it all the same. But in this case, we're declaring a variable called value. It's of type int. Then we're declaring a variable pi. It's of type float. We're initializing it to 3.14159. And the variable type cost to 9.95. We then assign the value that's in pi to the variable value. And so we're taking a floating point value and assigning it to an int. Most compilers will truncate, get rid of the decimal portion and just assign the whole number. And then we're doing it with a variable type cost, and we're displaying the value. So let's go ahead and run this program. And we can see that the variable value has a value 3. The C compiler just truncated the 0.14159, and it has a variable 9. So the C compiler didn't round up, it just truncated the 0.95. Assigning values from a variable one type to another type can lead to errors. And so we'll take a look later of how we can try to round variables up or round variables down so we can know exactly how the processing is going to occur. When we use modifiers such as unsigned long int or unsigned When we use type modifiers such as unsigned long int, our statements can get fairly long. And so as a shorthand notation, C allows us to define our own types. And so in this case, we're creating a type called ulint. And it's based on an unsigned long int, so ulint is just kind of an acronym. We made it in uppercase so we can kind of know that it's a special type, and we can then use it to declare a variable. And so it's kind of a shorthand notation, and you probably won't use it that often, but as you look at other C programs, you may see a typedef statement. So So we're creating a type definition, or you may see a variable that doesn't look like one of C's 4 basic types, int, char, float, and double. And so you're wondering, where did that type come from? Well, some programmers defined it using a type def statement. And so again, you probably won't use these, but you may encounter them in programs that you evaluate. So programmers use typically decimal values on the base 10 numbering system, but they can also use octal values and hexadecimal values. And so when we create a variable, we can assign an octal or hexadecimal value. And to indicate an octal value, we precede the digits with a 0. So in this case, we're assigning the octal value 1, 2, 3, and the hexadecimal value we precede with a 0x. Then we can use hexadecimal digits, which can be the letters A through F, or numbers 0 through 9. And so again, you won't be doing this in any of the programs we create early on, but you may see an assignment operator code that you're looking at and saying, what's the 0x and why does the values have letters? Well, it's a hexadecimal number. So we've discussed the fact that a type defines a set of values a variable can store, as well as a set of operations the program can perform on that variable. And so in this case, our program is going to declare a short integer variable called positive. And so behind the scenes, the C compiler allocates memory to store that variable. And in that memory, it's going to use a bit to represent, is this a positive number or is it a negative number? We call that the sign bit. And if we try to store a value that's bigger than the remaining bits can store, something called overflow occurs. And so you just need to be aware of overflow because it can lead to bugs that are hard to detect. But let's look at this program. A value of type short int can store values in the range minus 32,768 to 32,767. That's its value range. And so in this case, we're declaring a variable called positive, and we're assigning it 32,767, the largest positive value a variable of type short int can store. And we'll display that value. Then we're going to add 1 to it. And when we do that, we're going to exceed the size of the variable. And so if we were to look behind the operation at the bits that were actually happening, we'll see that the very leftmost bit is called the sign bit. If it's 0, the value is positive. If it's 1, the value is negative. And so if we have our value 32,767, you can see it's used all the storage. They're all 1. When we add 1 to it, we change the sign bit and the number becomes negative. So although we're dealing with just positive numbers, when we run this program, we see that adding 1 to that big positive number causes it to become negative. That's called overflow. As you work with programs, you'll eventually encounter an overflow error, and it'll be one that's hard to debug, but that's what's going on behind the scenes. So precision defines the accuracy to which a variable can store a number. And a floating point number, a variable type float, has about 7 digits of accuracy. A variable of type double is about double that, so about 14 digits of accuracy. So you can see that our program has defined 2 variables, one of type float and one of type double. And it's assigned a very specific number to each. But when we print or run this program, we see that we're accurate with the floating point number to about 7 digits. You can see it goes 1, 2, 3, 4, 5, 6, 7, 9, and then a bunch of nonsense. Whereas the double precision is accurate to more decimal positions. And so if you need to be very accurate with your representation of a number, you should use double precision variables. You might ask, why don't I always just use double? Well, double can store double the accuracy, but it also takes double the amount of memory. And so it's consuming more memory, and it's also then slightly slower than a variable of type float. But you need to keep precision in mind, because just because you want to store a value doesn't mean that behind the scenes the computer can represent that value as accurately as you need. As you examine C programs, you may encounter something called an enumerated list. And an enumerated list is a list that contains specifically named items. And so in this case, we have an enumerated sports list. And it lists the sports: basketball, baseball, football, soccer, and game. And so we can use the items in our list just by name. And they're kind of treated especially behind the compiler. We didn't have to declare them other than to include them in our list, but they're meaningful. And so in this case, we're declaring our list. Here's the sports that are possible. And they're saying, what game are we watching? We're initializing it to basketball. Basketball is known to the compiler because it appeared in our enumerated list. So we can treat it somewhat like a variable name. And so we, in this case, we'll check what game was assigned, and we'll display a message that corresponds. And so in this case, it looks at the game and says, oh, the game is basketball. My favorite player is Michael Jordan. If we assigned it the game of football, it might say my favorite player is Troy Aikman. And so you won't be using a enumerated list in any of the programs that we create in this course, but you might see them in programs that you examine. And so an enumerated list contains one or more meaningful names. And so we have our sports enumerated lists: basketball, baseball, football, and soccer. So this code's pretty readable. We know we're talking about a specific sport. And so someone reading our program says, okay, I get it. Thank you for giving me a meaningful list. We can then use that list throughout our code in different ways. In this case, we're going to loop through the available sports and display messages about them. And so this uses a for statement, which we'll look at later in this course. It uses a switch statement. And so again, I just want you to keep enumerated lists in the back of your mind, because you may see them in other programs. We won't be using them right off the bat, but when we run this program, it loops through our list and displays the corresponding favorite players. So a few more words on enumerated lists. Behind the scenes, the C compiler assigns a value to each one of the items in the list. That's how it's keeping track of things. And so in this case, we're going to display the values that the C compiler is using for each. When we run this program, we'll see the following output. Basketball's got the value 0, baseball's got the value 1, football 2, soccer 3. And so when we work with enumerated lists, there may be times where we want to assign a specific value to each one of the members. So in this case, we defined our enumerated list and we said we want basketball to be 10, baseball 20, football 30, soccer 40. And that's just because of how we're doing processing in other places in our program. But in this case, when we run our program, we'll see the corresponding values that the C compiler has assigned to each one of the items in the enumerated list. And again, you're not going to see enumerated lists often early. So we've made it through types and variables, and what you need to know is that to store data as they're executing, programs use variables. And each variable has a type, integer, float, char, double, that defines the set of values the variable can store. And it has a set of operations that you can perform on the variables, such as addition, subtraction. And so in the next lesson, you'll learn that C programs make extensive use of the printf function to display output. We've used printf to display hello world and other messages, but often we'll need to display character strings, integers, as well as numerics. And so in this case, we have a printf statement, and we tell printf the types of values that we want to display. I'm displaying an integer value. I'll use the %d format specifier to tell printf, hey, this is an integer. I've got the value 3.14, a floating point value. I'll use the %f format specifier to tell printf it's a floating point number. And then I've got a character string, so I use %s. In the next lesson, we're going to dive deep into these, and you'll become very comfortable with printf.